pulls. The Earth pulls the moon. The sun pulls the Earth. You fall because the planet drags you downward. Simple, obvious, completely convincing, and not quite true. Here's the strange part. When you stand on the ground, you feel a force in your feet, but the falling object next to you feels nothing at all. Drop a stone, and during the fall, it experiences no force, no tug, no sensation of being pulled. The only thing feeling a force is you, standing still. That should already bother you, because if gravity were really a pull, the falling object should feel it most strongly. Instead, the one resisting motion feels the force. Einstein noticed this and realized something radical. Falling objects aren't being pulled. They're following the straightest possible paths in a curved space-time. The ground interrupts that path, and that interruption is what you feel as weight. So gravity is not a force in the usual sense. It's geometry. And once you see falling as natural motion rather than being dragged downward, the entire picture flips. The Earth isn't pulling you. It's preventing you from going where you already want to go. Let's start with something so ordinary you've never questioned it. Take any small object, a coin, a pen, your phone, and drop it. It accelerates toward the ground, faster and faster. Everything about the motion screams that a force must be acting on it continuously. That is the story you learned. Gravity pulls. But physics asks a more interesting question. What does the object experience during the fall? If you could ride along with it, shrink yourself, and hold on to the coin, you would feel weightless. Your arms would float. Your stomach would not drop. There would be no sensation of being dragged downward. The falling object feels absolutely nothing. This is not philosophical language. It is measurable fact. Astronauts orbiting Earth feel it constantly. Skydivers feel it before air resistance builds. A freely falling elevator passenger would feel it instantly. Now compare that to standing still. Right now, wherever you are, you feel pressure. Your feet press against the floor. The chair pushes into your back. Muscles maintain tension. Every second of your life, your body experiences force. So here is the paradox. The object moving rapidly feels no force. The object not moving feels one continuously. That should bother you, because forces normally cause motion. Push a box and it moves. Stop pushing and it stops. But gravity behaves in reverse motion, happens without feeling force, and force appears when motion is prevented. Already the word pull begins to sound suspicious. Standing still is the strange motion. We instinctively believe rest is natural. Falling is dramatic. But physics reverses that idea. When you stand on the ground, the Earth's surface pushes upward on you. That push travels through your legs, spine, and muscles. The sensation you call weight is literally the floor resisting your motion. Remove the floor, the force vanishes instantly. Gravity did not turn off. The resistance disappeared. The falling object continues smoothly because nothing blocks its motion. So the presence of force is not evidence of gravity acting. It is evidence of motion being stopped. The elevator thought experiment, imagine a sealed elevator floating far from all planets. Suddenly, rockets beneath it ignite and accelerate upward. Inside, you feel weight. Your feet press into the floor. A dropped key falls downward exactly like it does on Earth. You cannot tell whether you are standing on Earth or accelerating in empty space. This is not coincidence. Gravity and acceleration produce identical experiences. This is Einstein's equivalence principle, the starting point of the entire theory. Standing in gravity feels the same as being pushed upward. The first reversal. So reinterpret everyday life. Maybe Earth is not pulling you down. Maybe the ground is pushing you up. The falling object moves freely along its natural path. You are the one constantly forced away from that path. Weight is not gravity acting on you. Weight is the floor preventing your fall. Free fall is rest. We think falling means motion caused by force. Physics says free fall is motion without force. An astronaut orbiting Earth, a dropped ball, and an object drifting between galaxies are all doing the same thing, moving naturally. Near Earth, natural motion happens to head toward the ground. Not because something pulls you there, but because that is the straightest path available in space-time. The first realization, so gravity starts to look different. Not a tug, not a rope, not an invisible hand dragging objects downward. Instead, objects simply follow natural motion and the Earth gets in the way. The force you feel is not gravity. It is the ground refusing to let you fall. A falling object feels no force. A stationary object does. That already weakens the idea of gravity as a pull. But Einstein realized you can push this idea much further to a point where the old picture completely breaks. He imagined a simple experiment, not with telescopes, not with planets, just a small closed room, a room in empty space. Picture yourself inside a perfectly sealed elevator floating in deep space, far from stars, planets, and galaxies. No gravity anywhere nearby. You release a coin. It floats beside you, exactly as expected. No weight, no falling. Everything drifts peacefully. Now suddenly the elevator's rocket turns on and begins accelerating upward. Immediately something changes. Your feet press against the floor. The coin drops to the ground. Objects behave exactly as they do on Earth. Inside the elevator, every experiment you perform gives the same result as standing in gravity. And here is the key point. You cannot tell which situation you are in. Are you standing on Earth, or are you accelerating through empty space? There is no experiment inside the room that reveals the difference. The equivalence principle, this observation became one of the deepest ideas in physics, the equivalence principle. Gravity and acceleration are locally indistinguishable. That sounds innocent, but it destroys the idea of gravity as an ordinary force. Because if gravity were truly a pull from a distant object, you should be able to distinguish it from simple acceleration. Yet you cannot. Standing on Earth feels identical to being pushed upward in empty space. So maybe gravity is not a force pulling you downward. Maybe the ground is pushing you upward. Rethinking weight. We turn now to everyday life. When you stand on the floor, what you feel is pressure in your feet. That pressure is a contact force, the same kind you feel when leaning against a wall. The ground prevents your motion. The moment the floor disappears, if the elevator cable snaps, the force vanishes instantly. People inside float together. Gravity did not turn off. Only the resistance did. This means weight is not caused by gravity acting on you. Weight is caused by something stopping your fall. The natural path, so what is the falling object doing? It is simply moving freely the same way an object drifts in empty space. In physics, motion without force has a name, inertial motion. Near Earth, inertial motion happens to head toward the ground. The falling ball is not being dragged downward. It is following its natural trajectory. The ground interferes with that motion. The interference is what you call force. Standing is continuous acceleration. This leads to a strange conclusion. You think you are standing still, but physically you are constantly accelerated upward by the floor. Your body wants to follow the same motion as the falling object. The Earth's surface prevents it every moment. So the quiet state standing requires continuous force. The dramatic state falling requires none. Our intuition has it backwards. The second realization, so now we have two clues. Free fall feels like no force. Acceleration feels identical to gravity. Together they suggest something radical. Objects are not pulled toward Earth. They are following natural motion, and Earth simply blocks the path. Gravity might not be a force at all. A falling object feels no force. Standing still requires force. Acceleration and gravity are indistinguishable. So the obvious question appears. If nothing is pulling objects downward, why do they move toward the Earth at all? Why doesn't a dropped ball simply drift off in a straight line? The answer begins with something we almost never question. What is a straight line? The hidden assumption. In everyday life, straightness feels obvious. Stretch a string straight. Drive forward straight. Draw with a ruler straight. But all of these assume space itself is flat. We never notice that assumption because around us space behaves almost perfectly flat. Yet nature does not promise that space must always behave that way. Imagine a tiny ant walking on a giant globe. The ant walks forward without turning. From its perspective, it moves straight, but eventually it returns to where it started. To an observer outside the globe, its path is curved. To the ant, it never turned once. So the path can be straight locally but curved globally. Straightness depends on the geometry you live in. Einstein's question. Einstein asked a bold question. Maybe falling objects are not pulled off straight paths. Maybe the paths themselves are curved. Not curved inside space, but curved space itself. So the falling ball is not deviating from straight motion. It is following the straightest possible path available in a curved space-time. No force needed. The geodesic. In curved geometry, the straightest path has a special name, a geodesic. Airplanes crossing Earth follow geodesics. Their routes look curved on maps because the map is flat while the planet is round. Objects near Earth behave the same way. They move straight through curved space-time, and that motion leads toward the ground. The object is not pulled downward. It simply follows the geometry. Why you feel weight again. Now return to yourself standing on the floor. You are not allowed to follow your geodesic. The Earth's surface blocks it. The ground continuously pushes you away from your natural path through space-time. That push travels through your body as pressure. That pressure is weight. So weight is not gravity acting downward. Weight is the ground resisting motion, orbits without pulling. This explains something even more mysterious, the moon. We imagine Earth pulling it inward endlessly. But in this picture, the moon is just moving straight through curved space-time. Its path bends around Earth the way a straight path bends on a sphere. No invisible rope, no constantug, just geometry. The moon keeps missing the Earth because space-time curves beneath it. The third realization, so motion near Earth no longer requires a force. Objects follow straight paths. Space itself is curved, and those straight paths naturally lead toward the planet. Force only appears when motion is prevented. The falling apple, orbiting moon, and drifting astronaut all do the same thing, move freely. The Earth is what interrupts. Up to now, you might still hold one last belief. Fine, maybe heavy objects follow curved paths, but surely gravity still pulls on mass in some way. Then nature removes that escape completely, because light bends too, and light has no mass. So if gravity were really a force pulling on matter, light should ignore it completely. There is nothing to grab, nothing to tug. Yet the universe refuses to cooperate. Starlight passing near the sun shifts position. Galaxies appear stretched into arcs around massive clusters. Black holes trap light entirely. So whatever gravity is, it acts on everything. Not just matter. The old explanation failed. Before Einstein, physicists tried to keep the pull idea alive. They guessed maybe light particles had a tiny effective mass. If so, the sun's gravity could pull on them slightly as they passed. The math almost worked, but not quite. The predicted bending was only half of what was observed in the sky. Nature insisted on a stronger effect than any simple force could provide. Something deeper was happening. Straight paths in curved reality. Light always travels along the straightest possible route available to it. But if space-time itself is curved, the straightest path is curved too. So light doesn't turn because a force drags it sideways. It turns because straight itself is no longer straight. The geometry changed. Just like a straight line drawn across a globe looks curved on a flat map, a straight path through curved space-time looks like bending motion to us. Time is part of it. The most surprising part is this. Gravity doesn't just bend space, it bends time. Clocks closer to massive objects tick slower. Because light must always move at the same local speed, differences in time flow affect the direction the light travels. Part of the bending comes from curved space. Part comes from warped time. Together they create exactly the amount of bending we observe. The solar eclipse test. In 1919, astronomers tested this during a solar eclipse. The sun's glare vanished, revealing stars behind it. Their apparent positions shifted slightly, exactly as Einstein predicted, not Newton. This was the first direct proof that gravity was not a force, but geometry. The universe was not pulling light. It was shaping the path light naturally follows. The fourth realization, now everything behaves the same way. The falling apple, the orbiting moon, a beam of light near a star, all follow straight paths in a curved space-time. Nothing is dragged, nothing is tugged. Objects simply move naturally within the shape of reality. Force appears only when motion is blocked. Falling objects feel no force. Standing objects do. Even light follows the same rule. But this leads to the strangest consequence yet. The natural state of motion is weightlessness. Everything you have ever felt tells you the opposite. The astronaut illusion. Watch astronauts inside a spacecraft orbiting Earth. They float gently. Tools drift beside them. Water forms spheres in the air. We casually say they are in zero gravity, but that is wrong. Gravity there is almost as strong as on the ground. The spacecraft has not escaped Earth's influence. In fact, gravity is exactly what keeps the spacecraft in orbit. So why do they float? Because nothing is stopping them. They are falling continuously around the planet. The ground curves away beneath them at the same rate they fall toward it. Inside, everything shares the same motion. No pressure, no resistance, no force. Weightlessness is not the absence of gravity. It is the absence of obstruction. Force means interruption. Now come back to your own body. You feel weight right now because the floor interrupts your natural path through space-time. Your body attempts to follow a geodesic, the same path a falling object follows, but the ground prevents it. Your feet push downward. The floor pushes upward. That push travels through your bones and muscles. Your nerves interpret it as weight. Remove the ground and the sensation vanishes instantly. Gravity remains. Resistance disappears. So weight is not caused by gravity acting on you. Weight is caused by the earth refusing to let you move naturally. Standing still is continuous acceleration. This leads to a strange description. You are constantly accelerating upward. Not upward through space, upward relative to your natural motion through spacetime. Your body continuously resists the motion it wants to follow. The quiet experience of standing is actually sustained force. The dramatic act of falling is effortless. Our intuition reverses reality. Orbiting is effortless motion. A satellite orbiting Earth behaves exactly like the falling coin, except its sideways speed is large enough that the Earth keeps curving away beneath it. It never hits the ground. Inside, everything floats because nothing interferes. This is the closest state to doing nothing the universe allows. Free fall is rest. Standing still requires force. Gravity does not make objects fall. Gravity allows objects to move freely. Weight appears only when something blocks that freedom. The earth is not pulling you down. It is preventing your motion. And, after everything we've uncovered, a natural reaction appears. If gravity isn't a force, why does the force idea work so well? You can predict falling objects with simple formulas. You can launch rockets using Newton's equations. Engineers build bridges assuming gravity pulls downward. And it works. So how can something so useful be wrong? Because it isn't wrong. It's an approximation. The map and the planet. Imagine navigating your city using a flat map. For short distances, the map works perfectly. Streets line up, directions are accurate, and you reach your destination easily. But travel far enough and errors appear. Airplanes flying across oceans don't follow straight lines on the map. They